Hey guys, today we will be going into chapter 20. This is more of a filler chapter. It's just some extra information, important information though, about your hypothesis tests and some ways that you can manipulate them. The first thing is a quick clarification about alpha values or your thresholds that you use in hypothesis tests. These are also called significance levels. So if you have an alpha value of 0.05, then you could also call it a 5% significance level. So you'll remember we have a choice whenever we run our hypothesis test. We have a choice to either reject the null hypothesis or fail to reject the null hypothesis. So taking an example, let's say we want to survey people in a college to see if they are in support of having more vending machines on campus. And then in reality, 40% of people are in support of the new vending machines, but you have been told that only 30% of people support the new vending machines. However, when you run a hypothesis test, you decide to reject the null hypothesis and say that I think that the information I was given was wrong and that the true proportion is not 30%. So here we have made a correct decision because the true population proportion is actually not 30%, and that gives us power. So when we correctly choose to reject the null hypothesis, we have given ourselves power. So power is what happens when you make the right decision. What happens if you make the wrong decision? So there are two different types of errors that you can make when you run a hypothesis test, and we can look at them through a table. So let's take an example to walk our way through the table. Let's say, considering what's currently going on, we are talking about the COVID-19 pandemic, and then someone walks in to get tested. You can only definitively prove that someone has COVID-19 rather than prove that they don't have it. It's like proving someone innocent again. So our null hypothesis when a person walks in is that they don't have COVID-19, and our alternative hypothesis is that they do have COVID-19. So let's first say that our null hypothesis is true. Our person that walks in doesn't actually have COVID, they just have a light cold and they're coughing. So looking in the column where our null hypothesis is true, when we test them for COVID-19, there's two things that could happen. The first one is that we reject the null hypothesis. So our test is somehow faulty and it marks someone without COVID-19 as having COVID-19. So here, our test has messed up and we have made a type 1 error. So this is the case where our null hypothesis is true in reality, but whenever we ran our test, we decided to reject the null hypothesis. So we made a type 1 error. So we said, you have COVID-19, when in reality, you do not. The other thing that could happen is that our test works as it's supposed to, and then our test says that this person does not have COVID-19, and in reality, they don't have COVID-19. So we have made a correct decision, which is why this box is lit up in green, and then we have maintained the status quo. We are keeping our null hypothesis, no assumptions have changed. Now let's look at the other possibility, that the alternative hypothesis is true. So we don't know it yet, but in reality, the person that just walked in has COVID-19, and we're going to test them to see if we can tell if they have COVID-19. So this is the true case. Our null hypothesis is false. Although we assume that they don't have COVID-19, they actually do. Again, there's two things that could happen. The first one is that we reject the null hypothesis. So we test this person, and the test comes back saying this person has COVID-19. So we say we are going to drop our original assumption that they don't have COVID-19. Here we have made a correct decision because we said this person has COVID-19 and in reality they do have COVID-19. So here we have rejected a false null hypothesis and we have given ourselves power. Again, another correct decision. The other thing that could happen is our test would again screw up, and then although the person has COVID-19, the test comes back negative saying no, this person doesn't have COVID-19, they can go home and get some cough medicine. So that is a type 2 error. Although the null hypothesis was false, we failed to reject it. This next part gets really conceptual, and it shows the balance between your significance levels, your power, and how your decisions affect what kind of results your test will get. So our alpha value is usually set as 0.05. And then you'll remember that whenever we run our hypothesis test, if the p-value we get back is under 0.05, meaning that if our null hypothesis was true, there is under a 5% chance that the observed data occurs, then we reject the null hypothesis. We can go back to our college example with the vending machines, where we are sampling people to see whether or not they're in support of having more vending machines on campus. This time, let's say that we were told that 40% of students are in support of the new vending machines. Let's say that in reality, this is true. So our null hypothesis is true. Our p is actually equal to 0.4. So as we go out and we take samples from the school, we can get points all over the sampling distribution, right? However, if we keep taking lots and lots of samples, there's definitely going to be some case where our numbers start to look a little bit weird. For example, if we go out and we sample a couple students and all of them are in support of the new vending machines. This is definitely possible. However, it just looks highly unlikely based off of our normal model. But what if that's the only sample we got? What if we were told that 40% of students were in support of vending machines, but when we went out, the only sample we got back was a sample where all of the students were in support of the new vending machines? If we only had that to go off of, we would think that the information that we got was faulty, right? So there we would likely make a mistake and say, no, the information we got was wrong, and then we would reject the null hypothesis. So this is where our alpha value comes in. If the normal model is truly centered around 0.4, then when we set our alpha value as 0.05, that means that 5% of the data in the normal model will fall in this part, so below our 0.05 mark. So we said that our true proportion is equal to 0.4. This is the information that we were told, and this is our null hypothesis. Let's say that this is actually true. So in reality, 40% of the college supports the new vending machines. But when we go out and take a sample, we get a data point back where no one supports the new vending machines. So this has a really, really low probability of occurring given that the true proportion is 0.4. So because the probability of it occurring has fallen below our alpha value, our alpha threshold of 0.05, we would reject the null hypothesis because the probability of getting such a weird sample is so low. So here we have made a wrong decision and rejected our null hypothesis even though it's true. So now let's think, since we have our normal model here, we set our alpha as 0.05, so that means that 0.05 of all data points on the normal model fall below this line. So that also means we have a 0.05 chance of getting a point down here. And if we get a point down here, then we reject the null. So we set our alpha value as 0.05. That means that 0.05 of all the data points fall below that line. And that also means that we have a 5% chance of getting a point down there. Because as we sample, we could get a point here, 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 here. But there's a 5% chance that we'll go down here too. So when we get a point down there, what happens? Since it went below alpha, that means we reject the null. But in this case, our null is true. That means that there's a 5% chance that we falsely reject the null. So because we set our alpha value as 0.05, there's a 5% chance that we falsely reject the null. And what is it called when we falsely reject the null? So if our null is true and we reject the null, that is a type 1 error. So putting that all together, your alpha value is 5% here, and your alpha value is your probability of making a type 1 error. So you think to yourself, isn't the goal to not make errors? No one wants to make errors, right? So why can't we just make alpha super small so that it moves down here and then we don't have to worry about making a mistake? That is where we need to consider case 2. If your null is false. But let's say this is the distribution that we were just talking about. So this distribution has turned into the gold model here. So still we have our null hypothesis set at p equals 0.4. But this time, the null is false. So although we were told that 40% of students are in favor of the new vending machines, that's not true. There's actually less students that are in support of the new vending machines. We don't know what proportion, but it's just some number p. And when we're running our test, we're going to go see whether or not we're able to reject the null hypothesis correctly. So because our null hypothesis is false, our goal is to reject it, right? So we have to find evidence to be able to reject the null hypothesis and then find that our true P is floating around somewhere out there. So we don't know what this P is. It's just somewhere out there in the cosmos in a spot that is not 0.4. So I've labeled my alpha threshold again. And now let's think. Because our 0.4 as our center is false, that means that when we actually go out and take samples, the samples will not mostly fall into here. They will fall into this distribution instead, our rose-gold distribution. So as soon as we get a point out here, we will notice here's our threshold, here's the point. That means something's wrong, so we're going to reject the null hypothesis. So in this case, if the null hypothesis is false, and we rejected our null hypothesis because we got a data point out here, what does that mean? That means that we have correctly rejected a false null hypothesis, and therefore we have given ourselves power. So therefore, all of the distribution out here that is below the alpha threshold is equal to power. So anything below this line is called your power in the true distribution. But you'll notice that some of the distribution is still out here. So it still overlaps with your gold distribution. Even though your true P is somewhere else, the points that you got over here didn't pass your alpha threshold. So you're just going to sit there and think to yourself, well, the points that we got, they seem to fit our original assumption because they haven't passed the alpha threshold. They haven't gone out here yet. So that means that we can just sit tight and maintain the status quo. We won't reject the null hypothesis. So what have we done here? Even though we're sitting on a false null hypothesis, we have decided to fail to reject the null. So that means we have made a type 2 error. You'll notice that I have labeled alpha and beta here. Your alpha and beta are basically synonymous. They're basically talking about the same line, but they mean different things. Earlier we said that alpha is your type 1 error probability. And so it's the probability that if the null is true, then we go past this line and accidentally reject the null. But what about your beta? Your beta comes into play when your null is false, and your beta applies to the true distribution. So this applies to the pink distribution. And if you go beyond the beta value, so beyond this line in the opposite direction, once we get a point out here, we'll think to ourselves, well, since our null hypothesis is over here, and we got a point over here that hasn't passed our alpha value, then we won't reject the null hypothesis. So even though we're sitting on a false null hypothesis, we won't decide to reject the null because it hasn't passed our threshold and it's still above our beta value. So going back to the true distribution, if we get something beyond the beta value, so any of this portion over here, we will accidentally fail to reject a false null hypothesis. So that means that everything out here is the probability of making a type 2 error. So anything past your beta line is equal to the probability of making a type 2 error. So that means your beta value is the probability of making a type 2 error. You won't need to know how to calculate your beta or your power, it's just your alpha that matters the most. But this is a really good visualization for knowing why you can't just make your alpha value super small. Because as you move your alpha this way, your entire line shifts to the left, and that means your power is going to get a whole lot smaller, and your beta, your probability of making a type 2 error, is going to get a whole lot bigger. At the same time, if you don't want to make a type 2 error, so you move your beta value this way, you're going to increase your power for sure. You're going to decrease your probability of making a type 2 error, but your alpha value is suddenly going to get a whole lot bigger, and so is your probability of making a type 1 error. So you always have to find a healthy balance between your alpha and your beta, which is why we always set it as 0.05. Not too big, nor not too small of a margin. And there are some cases when you have to prioritize one case over another, or when one type of mistake is less costly to make than another. So going back to COVID-19, if a person walks in and wants to get tested, there's two types of errors you can make, right? One kind of error you could make is to say that when the person walks in, even though they don't have COVID-19, we say that they have COVID-19 and give them treatment for it. On the other hand, we could also make a mistake by saying, although the person has COVID-19, our test came back negative, so we're going to believe that this person doesn't have COVID-19 and they can go home. So here's the two types of errors. Which one is more costly? In case 1, where the person doesn't have COVID-19 and gets tested for it, they might have some side effects due to improper treatment or false treatment of some sorts. But what about the person that we sent home? So this is the person that does have COVID-19, but we were unable to detect their disease. So they go home, they meet up with people, they infect other people, and suddenly we have a whole lot more people in the hospital. So in this case, the error we make when our person with COVID-19 does not get detected is a whole lot more costly than our first error where the person without COVID-19 gets diagnosed with COVID-19. With the person where we failed to diagnose their COVID-19, that would be a type 2 error, and in this case, this is an error that we want to make a whole lot less than the other type. So in this case, because a type 2 error is so much more costly than a type 1 error, then we would want to reduce the possibility of a type 2 error as much as possible. So in this case, because we really don't want to make a type 2 error, we would move our threshold this way to minimize this massive area of the type 2 error probability. And even though the type 1 error probability increases, we still find that this is less costly than letting people with COVID-19 walk around society. So that was a really sort of abstract and conceptual lesson. It's really not an easy concept to grasp. If you're kind of confused right now, that's okay. This really takes some thought over how everything works together. The main thing that you need to take away from here is just the types of errors, and then in some situations, what type of error would be prioritized over another, and then in these situations, what would classify as a type 1 error and what would classify as a type 2 error. So, thanks for watching. I hope you learned something. Peace.